I will show you our recent finding of this magnetic competition in this topological kagome system and the connection to the anomalous Hall conductivity. So this project, let me move, yes. So this project I've been doing in a strong collaboration with Professor Hassan's group at Princeton, and all the muon spin rotation experiments. So we have done a combination of different experiments, but what I'm going to tell you today is mostly the MUSR, muon spin rotation data, which was done at the PSI in collaboration with my the members of the MUSR group at PSI, and also the neutron diffraction experiments we have done at PSI, and the original crystals came from Professor Jia's group from China, and then also some samples were provided from the group of Pomiya Kushin at PSI. And the theory support comes from the Neuper's group at the University of Zurich. So why this system is exciting is because actually it combines interesting structural, magnetic, and topological properties. For instance, this system has the layered crystal structure with a cobaltine kagome lattice, and the kagome lattice itself, because of its unusual the symmetry and the geometrical frustration, it can host many interesting states such as flat bands, Dirac fermions, or spin liquid phases. And in this particular case, we have autoplane ferromagnetic ordering that was suggested from the magnetization measurements with a small moment of cobalt, about 0.3 mu Bohr. But we have the magnetic ordering that breaks time reversal symmetry. And what the DFT calculation shows that the system is half metal, and which means that the low energy states around the Fermi energy are all the spin majority states, so these are spin up states across the Fermi level. And you have these linear band crossings, and this number of band crossings, they form the so-called nodal ring in some mirror plane, which is protected by the mirror symmetry. And this nodal ring, but if you include the spin orbit coupling, what the calculation was showing is that these band crossings here split, but still one pair of band crossing remains. And these are the wild points, and the wild points appear relatively close to the Fermi level. Also experimentally, it was not shown, but the experimental evidence for this while loop or the nodal ring is I think, is there. But the presence of the nodal ring and the wild points make this system to exhibit a topologically non-trivial band structure, and now one can study. So it provides an interesting ground to study the interplay between this magnetic state and the spin orbit coupling and this topological band structure, and see what else we can extract from this interesting interplay between different ground states. And moreover, the system shows a large anomalous Hall conductivity, which I'll come back later on. So I don't need to introduce what are the well semi-metal, but here the one point that I want to make is that it's really a bulk, the whole ground state. So basically in the wild point, you have well nodes in the bulk and the fermionic state on the surface. So the combination of the bulk and the surface makes it the whole ground state topological, and which is different from topological insulators. And in that case, this opens the way for the bulk sensitive probes, especially the magnetic probes, to interfere and to study the magnetic properties, especially to have well points you need to break either inversion symmetry or time reversal symmetry. So if you have interesting ferromagnet and at the same time with topological band structure, you can study with neutrons or muon spin rotation and so on. So it opens up more possibilities from the experimental point of view. So the individual wild nodes is considered as a source or a sink of the quantity that's called Berry curvature. And so it's a monopole of the Berry curvature in the momentum space with different chiralities. So you can have negative or the positive monopole charge. And the Berry curvature is simply speaking is a magnetic field that can live in the momentum space. And if you have an ordinary crystal that has no inversion, that has inversion symmetry and also time reversal symmetry, it cancels out to be zero. But once you break one of them, then it comes into play, and then it also influences the electron dynamics. Okay, so the experimental quantity that is directly linked to the Berry curvature is anomalous Hall conductivity. So the intrinsic contribution to the anomalous Hall is directly linked to the Berry curvature, because the integral of the Berry curvature in the whole Brillouin zone. And then, so it means that if you can measure the intrinsic anomalous hole, is directly linked to the topological properties of the bands. And so the calculation for this system, this is now the anomalous hole conductivity, the energy dependent anomalous hole conductivity. So here near the Fermi energy, you have a extremely large value of the anomalous hole. It's about 1,000 inverse on centimeter. And this is a calculation that only includes the intrinsic contribution of the anomalous hole. So this is basically comes from the Berry curvature. And it was shown that the Berry curvature is mostly concentrated on this nodal, the whale loop or the nodal line. And though if you measure experimental, that was measured back in 2018 in the group of Claudia Felser, they've shown that this also experimental value is comparable to the theory, and it has a large value. But at the same time, below 100 Kelvin, the anomalous hole is independent from the longitudinal conductivity, and that's also hints towards the intrinsic nature of the anomalous hole. So basically, you have a large anomalous hole that comes from the intrinsic band-Berry curvature effects. So on top of that, the anomalous hole angle is extremely large in this compound. It's much higher than the other anomalous hole materials. And so you get the material that can host a large anomalous hole conductivity and anomalous hole angle. So now the question was, if this anomalous hole comes from the intrinsic band curvature, then we decided to look at the magnetic properties on the microscopic level, and then see if there is a connection between magnetic structure and this topological quantity such anomalous hole. Now what we learned from the muon spin rotation. So the muon is a local probe, and so you shoot the muon in the compound, and then you see locally the magnetic environment in the system. But the two advantages of MUSR in this particular system is that, so MUSR is volume sensitive, so you can study if there's inhomogeneity in the system. But also second, the MUSR is very sensitive to the small moment, and especially in this case, cobalt has is like 0.2, 0.2 mu, or even lower. I can show you from MUSR. And with neutron diffraction, it was extremely difficult to look at the magnetic structure. So from both point of view, the MUSR has advantage. So that was quite helpful for us. So now if I look, this is the muon spin precession in a small applied magnetic field, and then this amplitude of the signal is proportional to the paramagnetic volume. So what you do is at high temperature, you have the signal with large amplitude. You reduce the temperature, and again, you get highest amplitude. But as soon as you enter the magnetic state, you see a small magnetic fraction here. And then you lower the temperature again, increasing the fraction. But at some point, down to the base temperature, you get the signal with almost zero amplitude. There's only like 3% of oscillation. But you have nearly 100% of the sample is magnetically ordered. Then you have some narrow temperature range where paramagnet and magnet coexist, and I'll get back to that point later on. So you have 100% magnetic state, but we have no idea whether it's homogeneous or non-homogeneous. So what we do, we then do a zero field MUSR measurement. So there's no applied field, and then we look these muon spin oscillations here around this internal field that comes from the cobalt moments. You see a long-lived, very nice, coherent oscillation with a single frequency. And if you do a Fourier transformation of the signal, you get a narrow field distribution with an internal field, local field value of about 250 millitesla, and a narrow width of that signal, which means that the internal field is very homogeneous inside the sample. And that's why I call it like homogeneous ferromagnetic ground state. But now what happens if I increase the temperature? You see that at higher temperatures, there is clearly a second component that develops, and then you see it splits more. So they get separated at higher temperature. But if I model it more carefully, I see that I need to add already a second component starting from about 90 Kelvin. And then this, you see clearly the second component evolves, and then it takes most of the fraction at higher temperature. Okay, so now if I follow temperature dependence of this, the relative fraction of the two components, you see that the first component is more or less constant, and then above 90 Kelvin, it linearly goes down. But at the same time, the second component comes in, so it appears and it grows at the cost of the first component. But what is interesting that the second component disappears earlier. It's like 5 Kelvin earlier than the first component. And if I plot now the total magnetic fraction on top of that, you see it's constant. This was measured from the weak TF measurements. And then as soon as you lose the second component, then you have a small fraction of that first component, which is the ferromagnetic one. So the phase separation is more or less comes because we lose the first component. Now the main conclusion of that, the measurement, the qualitative conclusion is clearly below, there is a 3 different temperature regimes. So below 90 Kelvin is a ferromagnetic one that was already known in the literature. And the second, in the large temperature range, we have a coexistence, or let's say we have 2 distinct magnetically ordered regions that kind of phase separate. One is ferromagnet and the other one is something else that I come back to elaborate more on the origin of that one. But you have a large temperature range where these 2 magnetic states coexist. Finally, it goes to the paramagnetic state. And this was already a new insight into the magnetic properties, because people thought it's a ferromagnet all the way here, but it's clearly not. So there is a large temperature range where it's inhomogeneous. Okay, and then we have some novel state that appears. So before I comment and I show you our suggestion about this new magnetic structure here, I want to couple that to anomalous hole. But before that, one important point is that when we did the muon stopping site calculation, we see only one stopping site. So that is consistent with the one peak at low temperature. So, and what we also see, if you take the ferromagnetic state, but you can't, whatever counting you take within the same volume, it would not produce 2 magnetically inequivalent sites. So this counting would not produce 2 components. So clearly the 2 components we see is a phase separation. So it's the appearance of another state. And another argument in favor of the phase separation is that we have 2 different transition temperatures. They are slightly different, but still. But from the muon stopping site calculation, we clearly exclude the counting, let's say, is the origin of the 2 components. Now, how the anomalous hole scales with this magnetic, the observations. So this is anomalous hole is a function of temperature. This is what we measured on the same sample, on the same batch, for that we measured μsr. And this is from the literature. They're coinciding pretty well. Now, if I put the ferromagnetic fraction on top of that, you see that the anomalous hole conductivity follows very nicely to the temperature evolution of the ferromagnetic fraction. And then I can make this very nice linear scaling between the anomalous hole, which is comes from the topological property of the bands, and the ferromagnetic fraction, which is here. So to the best of my knowledge, actually, this is the first example where you can really quantitatively connect on a quantitative level, scale anomalous hole and the ferromagnetic fraction. Okay, so you have some magnetic competition here on the volume level, and then it drives the thermal evolution of the anomalous hole. Okay. Now, the question is, what is this novel magnetic state that gives rise to the separation of anomalous hole? So what we considered is maximally symmetric magnetic groups according to the group theory analysis and also DFT calculations. So in the first magnetic subgroup is the one that has 2 components. One is in plane. So if you fully count these spins, then you get in plane antiferromagnetic state. But in extreme case, you have out of plane the ferromagnetic ordering. And the second, so this is how you see on the kagome plane. And the second is 120-degree antiferromagnetic ordering that has only this in plane component here. So according to DFT, the energy of this is lowest. So this configuration is lowest energy, and energy of this is about 20 MeV higher compared to the ferromagnetic one. But still, they are pretty. The energies are pretty close. Then we thought maybe when you raise the temperature, the thermodynamics can change the balance, and then it can tip the balance in favor of the antiferromagnetic state because energy is pretty close to the ferromagnetic one. So having these structures in mind, we simulated the μsr data. So at low temperature, you can simulate the data only with the one component, the ferromagnetic component, with a moment size of 0.14 μ-Bohr. You see, it's relatively small at the moment. But at high temperature, combination of the ferromagnet and antiferromagnet lines up. So the simulation is combining these 2 structures can explain the data pretty well with two different moment size. There's a 0.11 for ferromagnet and 0.15 for the antiferromagnetic state. So the MUSR suggests that at high temperature you have this combination of two structures, distinct magnetic structures with distinct magnetic moments. And then what you can also do, you can really follow nicely the smooth evolution of these moments, which from neutron diffraction was not possible because of the small moment size of the cobalt, and you get these slightly different TCs for these two magnetic structure. Okay, so so this was a suggestion from USR. Now, how we can understand if you even have this antiferromagnetic structure, what should happen with anomalous Hall? So then the first principle calculation shows that if you consider this out of plane ferromagnetic state, you have the high value of the anomalous Hall, and but in this within the antiferromagnetic state, it should be zero. So that because of some symmetry arguments, it should not give any anomalous Hall. So what we see is anomalous Hall is dominated by that ferromagnetic structure, and then the appearance of this antiferromagnetic state could explain the disappearance of the anomalous Hall, because you are killing the ferromagnetic state and you favor the antiferromagnetic state. Okay, so combining this MUSR anomalous Hall and DFT, you can say that we have competition between these two states within the kagome plane, and the energies of these two structures are relatively close, and you can then control the thermal evolution of the anomalous Hall. So you can kind of control the topological behavior of the properties of the bands. So we call it thermal tuning of the Berry curvature effects. Okay, so the final proposal we have for the phase diagram is you have out of plane ferromagnetic state below 90 Kelvin, and then you have it's two distinct magnetic states with distinct topological response. Finally, it goes to paramagnetic state. So this was something that should be always considered. And there's more measurements coming also from magnetization already, questioning the ferromagnetic state and also proposing the novel state here. So from neutron diffraction, as I said, we could confirm the ferromagnetic state at low temperature with a moment size of 0.2 μBor, but not high temperature structure we could not resolve. If you look the temperature evolution of the lattice constants here, the lattice constants are relatively smooth, has smooth temperature dependence. But what we found, if you look the widths of the components, so it's the Lorentzian broadening of the peaks and the Gaussian broadening, you see that there is some increase, maybe below 170 Kelvin. This is proportional to the microstrain, this component, but while this broadening is inversely proportional to the crystal domain size. So there is some change across the magnetic transition temperature, which could point to some coupling between the magnetic ordering and the crystal lattice. That's all we could say from neutron. So the next thing, what we have done is we applied the hydrostatic pressure, but we could only go to 2.5 GPa because that's what the MUSR pressure cell allows. We could see the tendency of the reduction of the magnetic state, but we still have this mixture of two phases even up to the highest pressure. And then also with a very small magnetic field, you can tune and you can go to the fully polarized ferromagnetic state. So it could allow some quantum tuning of this anomalous Hall. But then later on, there was the measurements from the group from China, which showed that actually this mixed state survives all the way up to 20 GPa, and then finally it becomes paramagnetic where anomalous Hall goes away. But you need a quite high pressure to control this, but still this phase is there. And even more importantly, recently, that was a paper published in 2020, is a theoretical model that reproduces our high temperature antiferromagnetic phase by the analytical model. Or I'm not really expert in this theory here, but they claim that the high temperature phase is exactly what we propose, this antiferromagnetic phase. But on top of that, they claim that the antiferromagnetic phase also it has a zero charge conductivity. There's no anomalous Hall, but they claim that it should have a quantum spin Hall effect in this high temperature antiferromagnetic states. And it was I was happy to see that to reproduce the experimental data. And there was also that came more or less in parallel to our paper that also see exchange biased anomalous Hall that also relates to the frustration, magnetic frustration in this kagome lattice. And beside the fact that we see very nice thermodynamic response of the magnetic state and then a nice link to the anomalous Hall or the topological properties, there was another nice observation of the flat band near the Fermi energy. So this is the STM peak near the Fermi energy, and which was explained that it comes from the kagome flat band here, that is degenerated with the parabolic band, and then when you include spin orbit coupling, then the opens up the gap here, produces a non-zero Chern number and some Berry curvature effects for that flat band. And even more the calculation, and then we observed some unusual behavior of this as a function of magnetic field that was related to the some diamagnetism on the flat band. Also, the whole sample is ferromagnetic. Some the orbital diamagnetism can occur on the flat band that also comes. The diamagnetic moment is linked to the spin orbit coupling. Okay, so this moment is tied up with a spin orbit coupling, which itself determines the Berry curvature of the bands. So this also is a good example. Another example where actually interplay between the strong correlations, spin orbit coupling, and these topological properties can give rise to some new phenomena or new properties. Okay, so what we have seen from BSR is that we see evidence of the volume-wise competition between the two magnetically ordered states on the kagome plane in a large temperature range in this magnetic semi-metal. And we see a very nice correlation between anomalous Hall conductivity and the ferromagnetic fraction on the quantitative level. And so we conclude that this is actually the rare example where the magnetic competition between these two states can drive the thermal evolution of the anomalous Hall conductivity that comes from the topological properties of the bands, and mostly from nodal lines or from that flat band and so on. And with also compared with other measurements, STM, we can say that there is strong interplay between this interesting magnetism and the spin orbit coupled topological band structure. And so with that, I would like to thank for the attention, and I'm happy to take your questions.